Welcome to a lesson with Dr. Pal. Let's take a look at an integration problem now in multivariables. All right. So perhaps we want, this is a first example, all right, of this type of thing. So let's suppose that we have a function, a surface even, and we want to find the area underneath that surface. And let's keep it fairly simple, what we're looking for. And let's just consider if we're looking at we want to find the area under a surface that's over a square, even a unit square, one that way and one that way in the y. And let's suppose that we have something like the surface z is equal to x plus y. Okay, just something simple like that. So z equals x plus y is actually a plane. And you can think, let's see here, when x is 0, I mean, this is going to look like y equals, it's going to be like this, y equals z, and then similarly z equals x here. So we're going to get something, we have a plane going out this way, going down. So we're going to kind of be looking at the area underneath the plane over that. So let's think about how we might want to do that. Well, you could think about slicing. We've kind of done that idea before, and maybe first semester calculus, you can remember back. I mean, think about, you have a region base, and then maybe even if you had like, and suppose you have some kind of surface up here, and you can kind of look at cross sections. If you're going to go like this up to the surface and down, up to the surface. And if you kind of look at all these cross sections, and if you look at a cross section, you give it a little bit of width, okay, to make it a little volume piece, right? So make that a volume piece, okay? So suppose you were doing it this way. I mean, it looks like, okay, if we kind of coordinate our picture, it looks like that's like a dy right there. And then you have in here, you have an area, right? Now, so you have an area multiplied by dy to get a volume chunk. So it kind of looks like, we're integrating with respect to y, and y will go from 0 to 1, say. Then what we got to do is we got to figure out what the area is at a particular y value. So, and then we can, so kind of like this is like a volume chunk, and we're adding up all those volume chunks, right? I mean, that's a single variable calculus type idea. But how do you compute this area? Well, you can actually compute this area via an integral. That's really the only thing. We're going to replace a of y with an integral, and see what that is. Okay, so what this integral is, this integral will be, so we're going to find the area underneath this curve, which maps out the area right here, okay, the top of it, and down to the x-axis, because it's kind of like, because it's like in this direction, this supposes the x direction. So it's kind of like if we turn it, it looks like we have, there's our surface, there's the top of our surface. And we want to, and we're going from, looks 0, x is going from 0 to 1 here, 0 to 1, and we just want to find the area underneath this curve. So how do you find this area? Well, we could say this area is simply the integral from 0 to 1 under the surface. Well, the surface function is z, so this height is z, and what is z? Z is x plus y. So that's like so this function right here is z equals x plus y. Now, at this particular moment in time when we took the slice, y is a constant. So momentarily, we're going to pretend that y is constant. That shouldn't be too bad, and x is a variable. We've been treating variables one at a time as a constant, and that's really all we're going to be doing with the integrals too, just working it backwards. So in this case, this is going to be and you have a dx. Okay, so this right here is actually equal to the area at y. It's just that integral. So basically what we're going to do is we're just going to evaluate one integral and then evaluate the other integral with using the result of the one. So it's just like iterated integration. We just do one integral, and then another integral. We do two integrals, one after the other. And that's how we find the area under the surface. It's called a double integral, but all you're doing is you're just doing single variable integrals, just one at a time. So here and in here we have from 0 to 1, x plus y and dx. And this is your area with respect to y. Okay, and then you just kind of going through like that. In general, this is true. I mean, all we have to do is kind of, you know, especially if we're going on a box. If we're going in a box, this is fairly straightforward. We'll talk in another video about what do we do if it's not a box in the XY plane. But if it is, or a rectangle, it's very simple. You just have your coordinates highlighting your box, you know, and then make sure this, if this is y, make sure the dy is on the outside. If this is x, make sure the dx is on the inside. And then what you do is you just pop down your formula for z right here. Z is x plus y. Hey, this is how you find the area under the volume, I should say, the volume under a surface. It's just the equation of the surface, and you put a dx, dy, put your bounds for x right here. Ours were, so this is x equals 0, x equals 1. Put your bounds for y right here. Y is 0, y is 1. Okay, without any further delay, let's actually make the calculation. Enough talking about it. So let's go for it. It's just one integral after the other. It shouldn't be too bad. Okay, so for starters, we have 0 to 1, 0 to 1, x plus y. Okay, dx, dy. Okay, so this part right here, let's evaluate. Let's calculate this part. Treating y as a constant. So we just take an antiderivative with respect to x. So we're going to get x squared over 2 plus xy. And that's the antiderivative, treating y as a constant in this case, when we take the antiderivative with respect to x. Then we go from 0 to 1. And then we do this from 0 to 1 dy. Okay, so we calculate this. So we plug in 1 for x, right? Remember, this is an x equals and an x equals 1 for x. So we're going to get 1/2 plus y, and then plug in for 0, and then you just get 0. So you just get minus 0. So that was kind of nice. Okay, dy, and then we're going from 0 to 1. Okay, so we do the same type of thing. We take an antiderivative. It's just regular integration. 1/2 y plus y squared over 2, going from 0 to 1. All right, so we plug in 1, plug in 0. Plug in 0 is just 0. So we just basically just plugging in 1. When we plug in 1, we'll notice that we get 1/2 plus 1/2, which is 1. So it looks like the volume under the surface, x plus y, over the rectangle, the square, 1, 1, is just 1. And we calculated that using what's called a double integral. And we did it by just iterating the integration process. Thanks for watching.